Welcome to this new appointment of the 40 under 40 lecture series on combustion. I'm Alessandro Parente, and welcome to, I'm happy to welcome you to this new appointment. Today we receive Professor Sayaka Suzuki. She's an associate professor at the Institute of Science Tokyo, formerly Tokyo Institute of Technology in Japan. She obtained her PhD in chemical engineering from the University of Tokyo, and then she worked at NIST at USA for 3 years as a guest researcher, and then joined the National Research Institute of Fire and Disasters in Japan. She's currently working on large outdoor fires and urban fires in Japan, and she's the recipient of the 2017 Young Investigator Award and the 2016 and 2020 Best Paper Award from the Combustion Society of Japan. She has been director of the board of director of the Combustion Society of Japan, and she's also an associate editor for the proceedings of the Combustion Institute. She is currently chair-elect of the Women in Combustion Advisory Committee in the Combustion Institute. And so it's really my pleasure to have her here today, and she will talk about breaking down large outdoor fire spread processes, focusing on the interaction of wind and firebrand showers. Thanks again, Sayaka, and I give you the floor for your presentation.
Yes, so sorry, I'm sharing the.
Yeah. We can see
Yes. Thank you. Thank you, Alessandro, for introduction, and thank you, Alessandro and Salvatore, for inviting me to this cool opportunity. I was watching this webinar for a while, and I didn't really think I would talk about it, talk on this a seminar, but now I'm quite excited about it. I'm Sayaka Suzuki from Institute of Science Tokyo, and today I'm talking about large outdoor fire problem the world is having. So title is that breaking down large outdoor fire spread process, interaction of wind and firebrand showers. Wait a little bit. Oh, why it doesn't. Sorry, what's going on?
We see the first slide.
Yes, I know. And I'm trying to move the slide. Okay. Next slide. So I'm sorry about it. Before I started talking about my actual research topic, I would like to introduce the Institute of Science Tokyo. Since that Institute of Science Tokyo is established October 1st, 2024. It's about a year ago by a merger between Tokyo Institute of Technology and Tokyo Medical and Dental University. So if you know about Tokyo Institute of Technology, it's actually just pretty much the same university, but we merged, so we changed the name. Then I realized when I'm preparing the presentation, this is a Nobel Prize week. So I just decided a little mention about a Nobel Prize winners related to Tokyo Institute of Technology. The 2000 year a Nobel Prize in chemistry, Professor Hideki Shirakawa, he graduated Tokyo Tech, and in 2016, a Nobel Prize physiology or medicine, Professor Osumi is he is still the professor in Tokyo Institute of Technology. So then I probably shouldn't forget to mention 41st International Symposium on Combustion is coming to Tokyo. Combustion Society of Japan is preparing to welcome all of you, and deadline is coming maybe 4 or 5 weeks. So I hope everybody comes to Kyoto. That would be hot because of the season, but Kyoto is a really beautiful city. So I also would like to acknowledge my collaborator, Professor Samuel Manzero from Tokyo University. So the reason I started the research which I talk today is that because of him. When I was a PhD student, he visited my lab and talked about the wire-and-urban interface fire problem and the firebrand's problem. And then I learned he was looking for the postdoc or guest researcher working with him on this topic. I decided to take the opportunity. So even though then I left, I joined NIST and worked with him. After I left NIST, we still collaborate. We did pretty much all the experiments together. So the experiments I talk today is also done basically me and him and some helps. So there's another acknowledgement. I would like to acknowledge my funding agencies. My research is supported by JSPS and the Micron Foundation, and also Japan Science and Technology Agency is like hosting, providing me like two kinds of fundings. One is newly funded, so it's not related to what I talk about today, but it's actually related to wire-and-urban interface fire problem. So that fusion-oriented research for disturbing science and technology. And also I'm funded by like a AJ Core program, and that is the focusing on the Africa-Japan collaborative research. So here is the people I work with. One country is like South Africa, and the other country is Botswana. I'm quite happy in the sense like I work with those countries, which I couldn't before because I was working for the government. But like I'm working on wire-and-urban interface problem with them to trying to solve the problem in the Africa situation. And I also would like to quickly mention that my funny students of mine. And since we took this picture, I have 3 more students, but like I'm now doing research with all those funny students. So the question probably everybody has, and when you see the title, that what are large outdoor fires, and like why there are problems, since people hear about like wildland fires and like forest fires, but maybe they don't call it large outdoor fires. So the problem I'm working on and today I'm talking about is that large outdoor fires included like wildland fires or forest fires, or they actually have a lot of names. So all those kind of like fires and like wildland urban interface fires and urban fires, and also informal settlement fires, which pose a threat to the people. So I would like to focusing on the people, and I would like to think about like how combustion science could help this large fire problem, and which is like a problem to the people. So do we have a problem? Yes, we do. Ui fire was like really bad in 2025. So January, it started like LA was burning. Everybody saw that like January 6th, 7th, like there's like a huge fire was going on and everybody had to evacuate. And there was like more than 18,000 structures and a lot of burned area. Then like the end of February, Japan had another Ui problem. Yes, compared to the LA fire, there is like a lot less structure loss or like a burned area, but Japan did not have such a huge forest fire or Ui fire for like decades. So it was like a huge problem to Japan, and also that made Japanese think like we may have a Ui problem, which we thought we never did, kind of problem. Even though I was talking about Ui fire problem, Japanese people didn't really think that is a problem. So now, unfortunately, because of this, they realize that might be a problem to Japan too. Then March, South Korea had a lot of multiple wildland fire going on and a lot of people dead. and thousands of structure loss and huge burned area. Then May to June, Canada had multiple wildfires also happening in structure loss, and more than 1 million hectares was burned. So looking at Europe, July to August was a bad month for Europe regarding like wildfires or wild-urban interface fires. Of course, everybody was hard, like Greece people had to evacuate from island of Crete and Portuguese and Spain because of the heat. And as you can see in the map, there was fires reported within the past 24 hours on July 19th. Is that there is a lot of wildfire going on at the same time. Then looking at like historically, there isn't that much maybe UE fires, but in terms of large outdoor fires, we had a lot of urban fires. So since it's old time, we don't have the picture like an actual photo or anything. There is always drawings. That's like in 1659 of a Great American Fire to like a 1666 Great Fire of London. And 1871 Great Chicago Fire, they burned a city and a lot of people lost structures and houses. So what is actually issues with large outdoor fires or wildfires or oil fires or urban fires is that, yes, loss of lives. Sometimes like because they couldn't escape or fire was too forced and people dies. And loss of properties. So because of fire, hundreds or thousands like houses are either threatened or destroyed. And people have to evacuate. That cause some kind of problems, and smoke from wildfires or oil fires would pose risk to the people. So what we need to know. So we would like to know like how fire spreads so that we could evacuate effectively, or we could put the resource to fight the fire effectively. But before that, like we would like to detect the fire when it's small so that it's easy to deal with. Then we also would like to suppress the fire once it's or like even small or big. Then we also have to let people evacuate, and that has to be like effective and less confusing. And since it's burning, like there's always smoke. If you remember, there's like an image here is showing that like New York became so orange from the smoke from in the Canada wildfires. So in terms of smoke, it's not only like the wildfire burning near you is the problem, like a wildfire burning far away is also a problem. So depends on the like materials burned, like what kind of smoke can be produced. And also that smoke, how that can affect the people, we really need to know. And one thing I'm working on, and like I'm working with like Sam and Sarah from Forest Service, is that like a large outdoor fires and built environment working group and the International Association for Fire Safety Science. We're trying to see the problem like broadly, and we would like to get a lot of people involved, since this problem isn't about the combustion scientist or like a fire protection engineer or like an ecologist. Or not only that, we would need to involve like a social scientist or actual firefighters and practitioners, industry people, or like government officials, or everybody. So we are working on that, but today I, as like a combustion scientist, will talk about is that, and I'm interested in the, yes, how fire spreads. regarding like a combustion point of view, also what kind of smoke or like a particular molecule can be produced could be of interest, and I'm also interested in it, but I'm not much working on it. So I'm talking about like how fire spread. So I mentioned a little bit, my focus is actually the community. So how we can protect like a structure burning. So the the point is, so if you think like a wildfire is happening in the middle of nowhere, that other than smoke, it doesn't cause so much problem to the people. So you may not need to evacuate. You may not, probably you don't gonna lose the houses. But what I care is that like, so because of those large outdoor fires, how people would be affected. So how we can protect the people. So the issue is out of large outdoor fires like UI fires coming from like wildfires and like destroying like communities. So I talked about the examples and like that. So LA lost like thousands of houses and Korea lost thousands of houses too. So of course, like urban fire becomes like out of control. That is also cause problem. And informal settlement fires, where like they don't follow the building codes, but once it starts burning, they will burn a lot. So the common feature in the like while on the urban interface fires and the urban fires informal settlement is that structure to structure fire spread. If we focusing on the structure to structure, we can call that like a fire spread process are similar, so we may be able to work on the like comprehensively. So if we talk about like urban fires or like a urban area, everybody think like we should have some kind of codes and standards. Since by the time now it should be. So codes and standards are usually related to buildings or city plannings, which could extend to the urban fires. Those kind of codes exist. And unfortunately, informal settlement is not really following like codes and standards even existed. So regarding like large outdoor fires, like UI codes and standards exist but are limited. So like ICC or ACT International, like ISO is working on it, but it's not complete yet. And there's like ISO WG14 published the report on the global overview of different approaches to standardization, which includes all the urban large outdoor fires, including like UA fires and like urban fires, kind of like causing standards. So if you're like really interested, you can read it, but it's not much causing the standards or existing regarding like UI. Then if you're thinking about UI, like STM sponsored a workshop back in 2015 related to like UI fire standard cause issues. Then 2017, I thought like TC92 also had the workshop on large outdoor fires. Then they decided to work on it. They set up the TG3. That's kind of like a intermediate, some kind of group activity to actually set up a working group. And now they have the working group WG14 under TC192 for the topic like large water fires and the built environment, specifically working on large water fires. And also International Forum of Fire Research Directors realize the problem. So they also issue the position paper, they call forum International Forum of Fire Research Directors like issues a forum position paper every once in a while if there's something important fire research community should work on. So that is also published like 2018. then what we know still, unfortunately, is that like current UV fire standards cause a reflection of current or like a lack of like a science. So it's not like a causing standard doesn't exist, but our understanding of the UV fires are limited. So it's not really reflecting to the causing standards. So since I talked about the background, like I'm started talking about like how large the fires are spreading. So outdoor fire spread mechanism is just three-way: direct flame contact and thermal radiation and firebrands. Firebrands is a small burning flying object which could ignite onboard fuel when it's landing. So if you can think about the news, I'm sure you saw a lot of firebrands everywhere in the news articles in the like, related to like oil fires. So actually, direct flame contact and thermal radiation is studied a lot because that is also related to like urban fire problem, not oil fire problem. Even the firebrands is a problem, but it was least understand and like least studied compared to like other two direct flame contact and thermal radiation. But firebrands are the cause of structure loss and the cause of rapid fire spreads. Then if you think about it, as I said, like you remember the LA fire has like a you can see the firebrands are like a lining because of the exposure of the like, taking picture, and that's all firebrands. And I'm pretty sure this is too small to show now. I'm looking at it, but Meraki fire image, if you can going back to like several slides for me, but like later. So here is like a small black spots are already like in the like those pic drawings. So even though like a American fire era, they know firebrand's existence, but still that's how firebrands are igniting something is still the least understood problems. So let's talk about the firebrand processes in large-scale fires. And firebrands are usually generated from burning houses or like trees. While like of course like anything burning could produce firebrands, so it's not limited to like a house or the trees. And like because of the like plume or like other like forces, the small piece of like broken off from the houses or trees, then uh, lofted by the buoyant fire plume or pyrocumulus. The decently pyrocumulus is becoming a problem. Like it's more like a wildfire making their own weather kind of like a situation. Then since it's small, they would be transported by the wind, and then once it's landed on something, and depends on the situation, firebrands deposit on the unbound fuel, then accumulating, then igniting the unbound fuel. So that ignition itself could be like smoldering or like flaming, depends on the situation. So how we should approach those problems? Since the actual disaster is huge, it's like millions of acres could be burned at one time too. And that is one example I'm taking for the structure related to uh, stuff. And like, for example, you will do the investigation or you will learn from actual like a disaster. Then since in the Itoigawa City fires case, like uh, houses are burned. So we wanted to know what kind of firebrand could produce when actual house could be like burned. So we did like back in 2011, we did experiments, maybe 12 probably. So And then we did another kind of a much more simpler full-scale experiments. And then, but like that is still, you could call shed or like a house, kind of like a structure experiments. And then we did like a components experiments. So, but we don't know how small that could be. So we call it full scale like a experiment, full scale components only experiment. Then we made that the component smaller so that we could get the similar results or not. Then yeah, we don't have the standard test, but those kind of research eventually could lead to the standard test. Then yeah, if we have the standard test that working or not could be tested in the like real disaster. So we think of like this way and we could approach like that way, but the reality is just every single step requires reality check. So you burn the real house or we burn the full scale like a components like a component, then yeah, we just have to check with that's anything similar to what we see in the like, investigation, real disaster or real house experiment. So every single step like we take the reality check to like, we do the reality check to compare with the real disaster or like previous experiments, and what we do actually represent real disaster or not. Since otherwise we can just make it smaller experiments, not really reflecting the real world problems, but because the problem is too large and like, but we can't really bond the city or like houses to actually replicate the situation. So we just have to make sure what we do in the small scale is really could relate it to the like real situation. So in order to know what could be ignited and how it's transported, we need to really know like what kind of firebrands could be produced. So firebrand generation research, of course, structure houses are ignited and firebrand could be produced. But like before we start experiments, there wasn't that much data existed, like a firebrand production from structure. It did a couple of researches, but like that was it. But like from Auckland Hill fire to Sakata fire, and also recently I mentioned like Itoigawa fire, like firebrands were recorded. Now, firebrands are, as you know, like seen everywhere. And also most of the structure ignition in the large auto fires are like firebrands. So it's important we know like what kind of firebrands could be produced from structures. And also, of course, vegetation, trees and shrubs are ignited in larger fires, then firebrands could be produced. And because like in the like wildland fires, like spot fire distance is also important, and firebrands cause a spot fire, so it's really important to know like how far we could like estimate like how far they fly. So, but if you would like to investigate what kind of firebrand could be generated, the either one, we do some kind of experiments, or two, investigation on real fire. But either way, as you can imagine, like as data, it's limited. Since experiments, we usually do the controlled like a situation, and investigation on real fire. You can't go to the like a fire when fire is actually happening. So investigation is also always like a post-fire situation. So fire burns often could be like a just become ash and like nothing left, or like because of firefighting activity or because of like a house burn, like those fire brands also could be like already burned out too. So, but we just would like to know what kind of like fire brands could be produced. So first, like as I mentioned a little bit, we burned like a full-scale structure to investigate like a firebrand production. It's here, but like it's not easy to do since it's dangerous and also expensive and needs a lot of help. So we just needed to know something from simplified building components. So we decided to make it simpler, and we just wanted to know, and we investigate that could be, we can gain anything from like a simpler experiment. So we made it like a full scale, like a house born experiments, and we made like a structure with simple components, and we cut down some of the component and they burn too. So if we could make the experiment smaller, we could use those experiments to actually see, like, what if we could design or we could invent some materials to produce less firebrands, and we could test it. So it's just we needed to like develop some kind of experimental method. It's small, but also that experimental method could produce firebrands which similar to the like firebrands in real fire. So we made like a, in the bottom picture is like we made 1.2 and a 2.4 meter like a building component. So the question we had is that can we go even smaller? So we trying to develop a smaller scale experiments, and as I said, like the experimenter after we did like a house-born experiment, we did the component experiment, but we weren't sure how big that should be. So we decided to start with like a 2.4 meter and 1.2 meter, 1.2 meter corners. Then we felt it's too big. Anyway, it's taller than me, and like it was hard to control. So we tried like maybe like a quarter of size would be fine, and we developed the burner so that we could simulate the like same situation. So then we got like a firebrand, and we measured the mass and then projected the area of the firebrand. So we tried to compare under the same wind speed, and then we plotted the data, and that looks pretty okay, and like looks similar like a firebrand is produced. So then we wanted to know like how wind could affect on firebrand production. So we changed like a wind speed and did the similar experiments. So since it's important, if you would like to model the firebrand transport, what kind of firebrands could be produced? So we need to know. Then we also plotted with the projected area in the mass, and we got the value of the slope. At that time, we are calling value of the slope. Now we are calling that firebrand coefficient. And regardless of the experimental method, so we did the full-scale corner assembly, full-scale structure, and like a smaller experiment. We got the similar like a firebrand coefficient under the same wind speed. Then as the wind speed increased, like we realized the firebrand coefficient will become larger. So which means like usually like a heavier firebrands could be produced. So that transport behavior may be different. If you would like to model like transport, you should be considering those kind of aspects too. Then we thought about like, you know what, we developed like, we made it smaller and smaller and smaller using like simple materials. Then what if we use more realistic materials and we made it bigger? So we do the experiments with mock-ups, and we mock-up experiments by the method developed by like much more simpler materials. Then we are going back to the like full-scale larger experiments and compare the results. since it's important. So we tested with realistic materials. We chose Western red cedar sidings and the roof. Since that is still somewhat popular in the United States and it's famous producing firebrand, since as you can imagine, it's made from wood. But there is two kinds of Western red cedar sidings. One is singles and one is shakes. And we also tried a fire retardant and non-fire retardant materials. Since as you can see, those are wood materials, so they are recommended to put some fire retardant materials so that in the case of fire, it doesn't burn. So we did experiments and we compare the data. So good thing is when we did experiments and single siding, trend were relatively similar. If wind speed increase, firebrand coefficient increase. That's still we consider good results given how those realistic materials looks so different. But when we did the experiments with the shakes, it's much more funkier shape wood sidings. The wasn't going well a little bit. We're still working on what is the issue with this experiment, since as you can see, untreated shear sinking is increasing. Firebrand coefficient is increasing as wind speed increase, but other full-scale experiments, they decrease the firebrand coefficient. That is different from a single experiments too. So we're still working on to see what we are missing or what we have to know about that too. But overall, given other than certain conditions, we did the similar trend as a huge win for us to think about that method may has the possibility to work in the future. Then we also burned a tree under wind too. So it's not new to burn a tree under no wind actually, since it's famous a Christmas tree. If you are not careful, it's dried, it could be burned. So that concept burning a tree isn't so new, but firebrand collection from tree under no wind wasn't really published until 2008. Then later, 2021, we decided to work on the collecting firebrands from tree under wind. Since it was a little bit tricky to actually burn a tree under wind, we tried a lot of methodology, but we eventually settled with putting a T-burner with next to the trees and get ignition. So you can see the flame spread under wind in the tree under wind. Sorry. So that is a 3 meters per second. And once it starts burning, a whole tree could be burned 10 or 15 seconds. So, and that is really quick, but even under no wind, it is quick. So once it's dried, it's clear, a tree could be burned very quickly. And we also tried to see we could ignite a tree by tree, like real wildland fire situation. Then we tried to different distance between the trees, and one time but we couldn't get ignition. That is a wider distance, and that's half the distance, I think. But as you can see, even though after the 5 seconds, if it's successful, they started igniting downwind trees, and they got ignition. But in the case of non-successful cases, even though tree looks like it's covered by like a frame, it wasn't long enough to get actual ignition. So it didn't ignite even though the similar condition other than the distance between the tree. So the question is that like how much a tree burned? Let's just compare with the different methods and also the like no wind and like under wind. So when we burned a tree in the no wind, we used the burner and the ratio of like initial mass and the mass lost was like 0.6. So it's pretty similar. And like even under wind, our method proved like it's all burning, like we could burn under wind, no wind. So it is like our method is proven to be like we could actually burn tree. It does not really matter under wind. So that is a good thing since before that nobody actually ever could burn a tree under wind. So then like we also compared like how frame length could change in terms of the tree height. So as you can see, the like tree under no wind could going up to 2.5 times, but like under even 3 meters per second could go to like a 2 times like the height. So I could say like instead of like a frame going up, frame just go bended because of the wind, and that is like a interesting point like we should consider in the future since the how frame could be bended under the wind in terms of tree could be like a one way to understand how fire could spread like between like a tree and tree without like a surface fuel. So then the question is that like firebrands even look different or firebrands aren't different. So that's like some image from like a firebrands and then no wind and like 3 meters second. If it's like no wind, there is no those small leaves on the like firebrands, like all the like small leaves are like burned and nothing left on the like firebrand itself. But like if you burn under wind, you can see that there's like some unburned parts are left because of that. Compared to the projected area itself could become slightly bigger since it has a lot of like small leaves. Then mass is like slightly heavier since it's not really burned. So that's again like what's important is that like under different wind speed, different firearms could be produced. So that could affect transport behavior. That could affect the ignition behavior, and we are glad to know those kind of information. So then like we're gonna work on the like fire and transport aspects. So the one thing like is popular, and we were interested in can we predict fire and transport using machine learning? So we have one data set like there is like more than 10,000 firebrands in total. We have the information with like all the firebrands like mass and projected area and this thickness for each location. So we used this data to do some kind of machine learning. So we thought about it and we just like what's related to the like transport phenomena. So velocity ratio and Lenz's number, touch column, drag coefficient, like ballistic like coefficient, like a fiber density, and aspect A ratio. We picked up those kind of like physical features and decided to test on it. So that's machine learning tested. So there's a test data. We don't have the 3 meters per second, but there's like a 0 and clear part is 3 since we use machine learning to test it. So and also 6 and 9. Then we tried like different kinds of machine learning techniques, logistic regression, and SPM and random forest and XGBoost neural network. And like we found out like logistic relation may be good and the neural network looks the best. Then the number one is like, of course, neural network looks the best. So while logistic regression doesn't look so bad, but like others did not look good at all. Then SHAP analysis is like performed in order to understand what features are important. It turns out the touch score number and the lens number and the wind velocity ratio seems important. So with that information, we would like to develop some kind of mechanism, but like we also would like to apply what we got to different data sets. So we applied this like developed machine learning techniques to the firebrand generation data from like cedar roof assembly I explained like a while ago. So that is made from base-thing, underlayment, and western red cedar sidings. So one data is like a fire returned cedar sidings in 6 meters per second, and untreated like non-fire retardant cedar singles like 8 meters per second. So compared to the like previous data, it's quite different. It's realistic materials, and we tried with neural network, and that looks. Given the like variation of the data, I'm not saying it's bad, but like my student wasn't happy about it, and he said like he got the like SHAP analysis and he understand which features are important. He said he's gonna do the pins. So we worked on the like physics info neural networks techniques, and we picked like a touch score number, Reynolds number, velocity ratio, and we also added turbulence since it is supposed to become important. Turbulence is supposed to become important as the wind become messy. So we added those like four parameters as a physical laws, and we tried, and that's the results. And like Reynolds number just didn't do well, so it's divergent. So, but touch score number and like velocity ratio seems doing well. And also we combined those like aspects and we tried those. Then we also checked the which one is good or bad. And so far as the data we tested, the touch score number alone have the best prediction. And even though we expected like adding turbulence means something that we didn't get so much information from that, but this may be due to the experimental conditions. We did both experiments in the same winter now, which it has doesn't really have the like not doesn't have the turbulence. For the future application, we are expecting like a turbulence can be important, but we are hoping to apply our technique to like a other much more bigger like fire. So then I'm talking about ignitions by firebrands like in the end. So ignition induced by firebrands. So when firebrands could be flying or what is happening. So what we need. So we need wind, and we want firebrands would like to be like behave like in real fires. It's flying. Then we need repeatability. So we develop the firebrand generators, and we would like to ignite structures, but the structure is like big. So can we make it smaller without compromising? So we could cut off some important part from structure where ignition could happen and do the experiment. So that is the firebrand generator we called Dragon. Because of we wanted to make the smaller experiments, we have like two kinds of firebrand generator now. And one is used for much more larger experiments, and one is smaller experiments. So the smaller version is called Baby Dragon. So the question is like why we wanted to have the firebrand showers. Like we wanted the firebrands to behave like in the real fire that we call the firebrand showers. So this firebrand shower is dynamic and like it's changing. It depends on the time and like firebrand showers. Firebrands could arrive on the fuel bed and different time and different places, and so the firebrand could interact with each other, interact with the fuels, and then cause ignition. There is a research used the non-reacting heat, hot metal particle as like surrogates for the firebrands, or like one firebrand burning flames could be dropped, but we don't think that is a realistic situation. We wanted to see like the realistic situation. So if we have the firebrand showers, what we can do is that we can test with the structures. So for example, roof assemblies, you can see like a firebrands are going under the tiles, then igniting like under the tiles. So everybody was talking about like, roof ignites by the like firebrands, but roof tile is supposed to be tile and non-combustible, but that's how it could ignite. We could prove that. We could experimentally prove that. So because we understand how it ignite, we could have some idea how to prevent igniting. Since at this moment, like that button or like underlying like a seating is still combustible, we just think like that part could be covered with non-combustible to be able to protect from igniting by firebrands. So another good thing about like firebrand showers is that like mulch, like as you can see, like you use for the gardening kind of mulch with moisture. So even though mulch is like so wet, if you attack with firebrand showers, you can ignite. So the this graph shows like we ignited super wet like a mulch flaming ignition under 8 meters per second. Super wet is that if you touch that mulch, you could feel like really the water. Kind of wet stuff could be ignited like a firebrands. Because like a firebrand showers keep attacking the mulch and eventually get the ignition. So, and we also could see like how ignition happens. Yeah, there is like a one firebrand, another firebrand. It's not like they deposit at the same time, but because of the like wind and like the situation, both are still combusting. And eventually, we saw the like mulch and firebrands between them are like start flaming at the same time. So we could see the like the firebrands themselves are interacting with each other and like also interacting with the fuels and get ignition. So we also are interested in what if like there's a fire nearby and those like radiation coming from like a fire or anything could promote the firebrand ignition or not. And we saw the radiant heat influence under 6 meter wind experiments, and 8 meter we didn't see so much, but like we did confirm that radiant heat could like promote firebrand ignition too, and that work was featured in Science, and like I was quite surprised and like happy about that. So after we worked on wild, like how it's ignited, we just wanted to know like what is important parameter. So we need to know the like a firebrand flux, or like it does not really matter the like it's like how many like firebrands could be gathered locally would be more important. So we came up with like approach like unit 8 approach and localized ignition approach. So we calculated like heat balance from the combustion, and we realized that probably that what kind of area we could consider would be the important factors. So then we calculated total number of firebrands involved with ignition per unit area, then radiant heat panel per unit area. Then we have this right negative relationship. So we're gonna work on more for that. Then if we took two approach, how much difference we could see? So I calculated a heat contribution from firebrands to fuel beds, one firebrand, and using the unit area approach and localized ignition approach. Of course, when we use localized ignition approach, the number is low. In some cases, 10% of the value, but we think that is probably still overestimating, but it's less overestimating the unit 8 approach, and that would be a little bit closer, but the value is changing a lot because it depends on how it's contacting with the surface. The heat contribution could be overestimated or underestimated. So that part we are still working on to understand the situation. So the other stuff we are thinking is that, so what is important? So how long the fireman's heating the fuel bed is important, or how many firebrands exist on that fuel bed is important. Probably the correct answer is both, but we try to understand the effective heating time approach in number-based approach. We call that, and time is important or number is important. So I just would like to mention a one large firebrand it's not could ignite anything. Sometimes firebrand shower can ignite fire beds when a large one firebrand cannot ignite. So this is why I'm talking about heat is important or a number is important. So if you calculate heat contribution, of course, effective heating approach is more than a number-based approach. But if you're gonna think about heat loss, between sometimes firebrand is not arriving at that spot and and it burned out, but still heating a fuel bed. Then another firebrand arriving and start heating again, kind of a situation. But heat loss seems still similar, but while effective heating time approach is over a more than a number-based approach. Then I also compared with a heater and the firebrand showers during the experiments using cartridge heater and the firebrand showers. So if you calculate smoldering ignition delay time, we calculated the heat flux from firebrand showers and the cartridge heater. So of course, the time to ignition for the firebrand varies a lot, but it's more than you can calculate from the non-reacting heater. So that's something we have to consider when we would use the heater to represent a firebrand in terms of evaluating any fuel bed. So I would like to mention the baby dragon we've been using for the experiments became an ISO firebrand generator, which we are quite proud of, published in 2024 March, and also Combustion Institute kindly acknowledge our accomplishment and our website too. So the last thing we talk about is that since we made that firebrand generator ISO standard, and also I mentioned, I have the project with Africa, where we may be wanna adjust our firebrands to similar to the one from African vegetations, African structures. So currently we can produce so-called structure firebrands and vegetative firebrands. that is matching from the data from like States and Japan, but we have kind of like a needs to produce different with different distribution, fibrants with different distribution. So we calculated we could produce a new firebrand without breaking the dragon itself. So if we keep the feeding rate constant, like we figured like we can probably produce the firebrands, but we have to be careful. There's like a specific heat capacity of like wood, and also T ignition could be different, depends on the wood. So that keep in mind. We tried like other materials to produce firebrand. So we use like Western red cedar wood pieces representing like a burning structures. That is like a slightly bigger than not slightly like a lot bigger than like the one we are using for vegetative like firebrands. That's Douglas fir wood pieces. So as first step, we try not to add any wind. So the efficiency firebrand generated produce new size and mass distribution of firebrand showers. So we did experiments, three kinds of experiments. One is using that new materials, and the other is like a firebrand Douglas for wood pieces. Oh, it's chips, it says. And we mixed with it and checked how it changes. So there's like a mass distribution from Douglas wood pieces and Western red wood pieces. So the firebrands from those materials, and we also show like mixed materials, and but only portion of Douglas wood pieces and the Western red cedar wood pieces too. So anyway, like a peak isn't changing, but like if you compare the ratio, how much it's flying in each location, there like firebrands are transported slightly wider when it's mixed to materials. We are happy we could produce firebrands, and that left us a little bit of like a question. Then we also measure the ejecting velocity from like a firebrand mouse, so that we would understand what is the difference and how it's different. So as you can see, like the Douglas fir pieces have the smallest velocity, ejecting velocity, and followed by Western red cedars and like a mixed situation. We weren't quite expecting a mixed situation is gonna have the largest ejecting velocity per se. So we checked like we calculated with the force balance and calculated like this, and we compared with like a PDF. Then we realized even though if we are focusing on mixed situation, so the winds velocity should be like Douglas fir mixed and like Western red cedar. But if we separated Douglas fir and like Western red cedar from mixed situation, the distribution is become wider. So because of that, the mixed situation has a wider distribution. Then because of that, like that velocity is shifted. But look at this, we have to study more to understand the whole situation. So hopefully, like we can study more about that. So there's a summary, and I think I'm speaking too long. So I just gonna like speak really shortly. We did some experiments and like using under wind to understand like a firebrand generation. And we also tried machine learning techniques on firebrand transport that so far we say like worked relatively well. And firebrand generators was developed, and we are using that to produce new kinds of firebrands. And we are considering like to actually understand how to ignite by like a firebrand showers. So That's it, and thank you for your attention. And that's me hugging the dragon, looks happy doing experiments. And like if you're interested in like wire on the fires or we fired, there's encyclopedia and so you may be interested to read that. And thank you, and that's it.
Thank you. Thank you very much, Sayaka, for this very interesting talk. Yeah, now the floor is open for questions. So if anyone would like to ask a question, please feel free to unmute yourself and ask. In the meantime, I have a question from Alessandro Parente, who had to leave for another meeting, and he was curious about, yeah, I'm gonna say his question, ask his question. He was wondering about how these reduce order models that you show you will take into account the wind, because I saw that you have a Reynolds number, but there is more. There is, I think, a lot more into that. Like there is the direction of the wind, recirculation zone that might create, and what structure are involved, and yeah, what's the and related to that, if I may add. I don't know if there are numbers that I show, but I didn't catch. I was thinking if anything like a BO number would also appear in that. If there is, that I didn't catch it, or if there any reason why there's no like a BO number in those models. So yeah, to that.
Okay. Could you tell me again? I'm sorry.
Yeah. Okay, no, just the first part will be just how to include in the wind also in this reduced order model. I have to take into account the effect of the wind in those models that you show in the particularly the machine learning part.
Machine learning, yeah, we included like a wind effect as like a Reynolds numbers so far.
And sorry, go ahead.
Yeah, no. Since that's the easiest thing to first working on that, but like we don't know why it doesn't work well so far. Since like we thought it should work on better too, but like in the end like Tachikawa number, which is much more like it's not combusting or anything, but it's much more just flying debris kind of like a number worked better in the end.
Okay. No, I mean it's for sure it's a complex problem because they have different directions of the wind. Like I said, the circulation zone. And is there like?
Oh no. So different direction is that like because the data we used so far is in the like a relatively good like wind situation.
Okay.
So we figure at this moment we don't need to think about the direction. But like this is why in the later like we added some like turbulence terms to see like that would affect anything. So hopefully we can figure out.
Yeah. And is there any like BO number, the number that says how much if this firebrand if it's the ratio between the conduction inside the firebrand and the convection due to the wind, is there any sort of number like this to consider?
Yes, of course we could consider and we should consider, but it's this machine learning stuff was like a first step for us. So yes.
No, but that's very very interesting. Of course, apart from all you have, like you said, you have experiments, different scales, and this is very interesting. Lots of data actually, and that could be used and that can hopefully help in decision making. And if there are no questions from the audience, I will just be selfish and ask another question. In terms of decision making, what would be your suggestion about if you had to materials that are good to avoid, to prevent fire spreading, and this kind of, would you have any recommendation to decision makers, to builders and so on?
Oh, these certain materials known to just like produce firebrands or like a burn well. So I think I wouldn't recommend using that. But what's important is that like if you want to believe it or not, like certain parts of the structure like burns, and because of a firebrands, and it just really needs to address the issue, not avoiding it. So, for example, like Japan's case, since they want to believe roof don't burn, but like when like a fire happens by the firebrands, it always starts from like basically like a roof. So, but it's hard for them to accept what they believe it's not burning is burning. So.
Well, I guess on that, if there are no questions from the audience, I think we can conclude. We can, thank you, Sayaka, for your very nice talk. And thank you everyone for attending, and we'll see you hopefully soon for another appointment of this lecture series. Thank you very much, and have a nice evening, Sayaka, and a nice weekend.
Yes, thank you.
Bye-bye. Thank you.
Bye-bye.
Bye.